thank you for attending today's webinar. My name is Mitchell Robinson, and I am the Marketing Coordinator here at THERMTEST. Today's webinar will be on Triad Curves and geological engineering applications, presented by Dr. Daniel Cederkrantz. Before we jump into today's webinar, I would like to mention our upcoming webinars for the month of July. To register for these webinars, please visit our website at thermtest.com/webinars. Towards the end of today's webinar, we'll be having a Q&A session. If you have any questions throughout the webinar, please type them into the chat, and Dr. Daniel Cederkrantz will address them towards the end. Before I pass it off to Daniel Cederkrantz, I would like to speak a little bit about him and introduce him. Dr. Daniel Cederkrantz is an expert in thermal conductivity with a focus on transient methods. He is a graduate in engineering chemistry with applied physics and a PhD in material science with a focus in thermoelectric materials from Chalmers University in Technology in Sweden. And currently, Dr. Cederkrantz is the CEO of THERMTEST Europe AB. Without further ado, I'd like to pass it off to Dr. Daniel Cederkrantz.
Thank you for the introduction, Mitch. And welcome everyone to today's webinar, where we're going to talk about the TLS 100 and what you can use it for, and especially then dry-out curves. So a quick look at the agenda here. We start off with taking a look at the device itself and the needle probes we can offer with it. We will then have a look at the very important standard that it follows, ASTM D5334. We will also say a few words about calibration of this machine, because that's a topic that often comes up when discussing with users. There's much interest in how this is actually done and so on. So therefore, I will linger a bit on this. Then we will take a look at how you prepare your samples for testing. And once we know that, we can take a look at how we create dry-out curves. After that, of course, we come into the Q&A session, and feel free to type in questions anytime during the presentation so that you don't forget the questions, and then we will take a look at them at the end here. So I hope there will be at least a few questions so we can discuss them. Okay, let's move on to looking at the TLS 100, the meter and its needles. So you can see the picture of it device here. It's a handheld device. It's not very large. It's maybe something like 30 centimeters long. It's powered by several options for you. You can use batteries. You can use a power bank, the same type that you use to charge your phone with when traveling. Or you can hook it up to a computer or a power outlet through a USB cable. So you should be able to keep it powered when in the field quite easily. Even if you run out of batteries, you might even be able to hook it up to your laptop that you brought with you to keep it powered and to keep testing. The device is robust and light. It has an IP code of 52, so it's protected against dust and also dripping water. So that allows you to work with it in the field without too much worry that you will damage it by dirt or rainfall perhaps, even though you should take good care of it, clean it up after testing and so on. Make sure that you don't get too much dirt in the connectors. That might be an issue or hard to clean really. It comes delivered in a very nice carrying cage that keeps it dry and safe, and it's completely watertight. So you don't need to worry about being in the rain carrying it along with you. So the needles might be something interesting to discuss, of course. The TLS 100 always comes along with a 100 millimeter standard needle, which is for soil or soft materials, or perhaps also polymers. In the picture, that's the needle that you see second from the left with an orange color on it. This is always included, and it follows, of course, the ASTM standard that we will have a look at shortly. Then next to that, with a red band on it, we have the 50 millimeter rock needle. As you see, it's shorter, 50 millimeter. It's half the length of the 100 millimeter, clearly. It has a larger diameter, which makes it much easier to prepare a sample for testing if the sample is hard. It's significantly easier to drill a 4 millimeter hole in a piece of concrete than trying to drill a 2 millimeter diameter hole. So it doesn't necessarily completely follow the ASTM standard because of the length to diameter ratio, but other than that, it completely follows the standard. So it's ideal for hard samples, rock, concrete, asphalt, for instance, anything that you need to drill in. And then we have the optional 150 millimeter needle. You see it to the far right here in the picture with the color green. It is quite similar to the 100 millimeter needle, but the longer length allows us to also comply with the IEEE standard 442, which sometimes is requested by users or by the organization that orders the testing from you. So that's a good option to have if you run into that type of client. Then we also have a novel sensor, which is, we call it VCP, 100 millimeter needle. It's the one completely black. This does not only measure thermal conductivity and thermal resistance, it also tests thermal diffusivity. And since it tests both conductivity and diffusivity, we can calculate the volumetric specific heat, which is the density multiplied with CP. There are some limits to diffusivity ranges and so on, but this really adds very nice testing capabilities, otherwise not possible with a single TLS needle. So that's a brand new needle that we offer. Of course, the instrument also has onboard software, and you can see a couple of pictures here. As an example here, this is a test on a backfill material. You see the sample there to the right, and on the left-hand screen picture, you can see thermal conductivity reported, you see the thermal resistance, and you can see how you name your sample. That's basically our start screen where you run the test from, and where you quickly see the results when you have them coming in. You can get more details, as you see in the second screen picture here, where you can see temperature versus time plot. You can see your total temperature increase, and thermal conductivity, and a correlation factor. Basically, how well does our result line up with a linear plot? So we want to have a number as close as possible to 1 here for a good result. It also tells you the drift, which is important to know. This is the temperature drift. You don't want the sample temperature to vary when you test, but we will have a few more words on that. In addition to the onboard software, the instrument comes along with a companion software. This companion software allows you to download or export results from the machine to Excel, for instance, to view them on your PC, and to also do some basic programming of the machine to do automatic testing if you're in the lab. So that's a nice addition, and makes it very easy to use to download and look at your data on a PC for preparing your reports. Then a little bit on theory or things important to think about when working with a TLS instrument. First of all, when you do testing with a TLS device, the sample temperature must be at an equilibrium. It needs to be stationary. You cannot have a sample that is changing temperature. So if you do testing in the laboratory, the sample should have been in the room for quite some time to make sure that the temperature is nice and stable. If you're in the field and do tests, you should take care to where you do your testing. If you're in a trench, make sure you're perhaps in a shady area. Don't move a sample from the shade to the sun and so on, because this will change the temperature of your sample and influence your results. During a test, the needle is operating like a heating element, and it's heated up during entire test time, the entire heating loop with a constant power, more or less. The temperature increase of the needle is recorded using a centrally placed thermocouple. So we notice how the temperature rises in the machine, in the needle, and that gives an idea how it diffuses from the needle into your sample. And we can then plot the temperature increase versus the logarithm of time, as you see in the picture here. And this is what we use to find the thermal conductivity. We do remove the initial part of the contact resistance, the very first few seconds, and because there you have information about contact resistance and such, we want to know things about the bulk values, not the interface. So therefore that's removed. And then thermal conductivity is inversely proportional to the slope of the linear part of the curve. As you see in the equation, lambda is q over 4 pi m, where m is the slope. So we have an inverse proportion here. This is the very basic theory. To know more in detail about the theory, we can look at ASTM D5334. This is the main standard governing all testing using the TLS 100, especially when you test thermoconductivity of soil and soft rock, which is what the standard is written for. So this standard will govern when to use the method, how the apparatus is constructed, how samples are prepared. It gives you the testing procedure that you should follow to be in complete compliance with the standard. It gives you the calculations and data analysis, and it also mentions calibration. So if you are going to do testing with this method, we strongly suggest that you get a copy of the standard to be able to comply with it and know the limits and what's expected from you when using the method. So it's not a very expensive standard. I think you probably something like $50 or in that range. So if you're going to do a lot of testing, it's strongly suggested to get the standard. Which brings us to the calibration. The standard mentions that you need to calibrate your machine and so on, but it's very important to understand that with our TLS 100, the needles are factory calibrated. There is no calibration that you need to do or even can do. All the needles comes calibrated along with a performance certificate, so you know that the performance of the needle is what we expect. The calibration itself is stored in the needle, so you don't have to install any calibrations files or anything like that. As soon as you hook up a needle, you will have the device calibrated for that needle. All needle comes with a verification sample, which you can go back to and verify that your calibration is still good. And as a matter of fact, normally there should be no need for recalibration of your needle during the lifetime of the needle. However, sometimes you need to do perhaps verification of the calibration because of you're working according to some ISO standard that requires you have this revision of your instruments, for instance. We do offer such verification of calibrations, giving you a new performance certificate, and this might be useful for some of you. We do, of course, also offer recalibration when needed, but bad calibration, when you don't have the result that you expect from your when you test your verification sample, usually is a sign that a needle is damaged, and a bad needle should rather be replaced than you try to recalibrate it. So confirm your calibration on a regular basis, perhaps before and after each testing expedition you go on in the field. If you have questions about this or in doubt, contact THERMTEST or your distributor, or if you need to update your performance certificate, same thing, let us know. So how do you prepare samples when you work with the TLS 100? The picture here shows you that you can, yes, you can of course test in the field. The drawback of do testing in the field is that you have very little control of sample density, moisture levels, and so on. So often samples are extracted either in the field or brought to the lab. And in general, samples needs to be large enough. The standard recommends you 200 millimeter long samples, but of course the minimum needs to be at least as long as the needle because the entire needle needs to be in your sample at all time during testing. The diameter of the sample should be a minimum of 50 millimeter. You can test samples as collected or after conditioning. For instance, in the field, it's very common to use a sampling tube to extract the sample. That can be tested as it is, as an undisturbed sample, either out in the field or perhaps even better brought to the lab where you can control the temperature better. In the lab, especially if you bring a sample that has been collected using a shovel or something like that, you need to condition your sample to mimic the properties when you're going to use the soil or backfill, for instance. So you need to compact it to the required or desired density. So there are several ways to do compaction. So select the one that's appropriate for your setup. You of course needs to determine the mass of the sample and calculate the density after compression or compaction. And if you're in the lab, it's also strongly suggested to estimate or establish the gravimetric water content, basically what is the moisture level in your sample. The needle needs to come into your sample and it should always be inserted along the central axis of the sample. Otherwise, you might end up too close to boundary and get bad results as a result. You can either push the needle in, and then it's suggested perhaps to use a dummy. That's a fake needle or just a metal rod to probe the sample, especially if you know there are stones inside. You don't want to risk damaging your needle by pushing the needle hard into a stone. So this works fine for soft samples. If the sample is really soft, no stones and so on, just push the needle in. If it's a stiff or hard sample, it can be a really stiff clay, for instance. It's almost impossible to push the needle in. And you need to drill a hole, which should be the same diameter or perhaps just a tiny bit smaller than the needle. And you push the needle in using that. If you drill, be careful. And if you can, use a press drill, because if you drill by hand, it's very easy to move the drill around a bit and generate voids or air gaps, which will be an issue for your results. So take care if you pre-drill. And then, of course, before proceeding with your testing, allow the temperature stabilize. If you drilled, you have generated heat. If you have handled the samples, temperature can also change. So take care with the temperature. It's very important that you don't have a temperature drift. Now we have prepared the sample and we are ready to test it, and we want to prepare a dry out curve. So why would we make a dry out curve? First of all, this is just a rough sketch showing a dry out curve where you can plot on the x-axis the moisture level of your sample from dry to moist, which will give you thermoconductivity from insulating to conducting. So this is typically an application, something that you do when working with high power cables, because they can, of course, not be allowed to overheat. So the backfill around your cable, it needs to be able to conduct the waste heat away from the cable to prevent this overheating. So as you see in the sketch here, a very dry backfill will be much more insulating than a moist backfill. So therefore, this is your kind of a worst case scenario, as we say. And of course, it's a worse thing to be in an arid environment. So there we need to take more care and perhaps select the backfill with bigger care. So we can move this curve around a bit by working with the material structure. Perhaps you can have a material that allows or is better at keeping the moisture. Or perhaps you can change the structure of your backfill material to move this curve up and down, to shift it up and down. So the 100% dry is our worst case scenario. So that's something that you can measure to make sure that if the completed dry sample is conducting enough, well, then you're out of risk. If you cannot manage this, then perhaps your trench needs to be deep enough to make sure that you never go that dry. Because if a trench is deep enough, there should usually be some moisture around to increase the conductivity. And just an important note before showing our procedure for doing this, you should always consult your local standards and regulations. Those can supersede our guidelines or the ASTM standard, for instance. There are sometimes also project descriptions for your testing, which will ask you to test outside of the norm for some reason. And of course, these things are something you need to take into consideration, and it's your responsibility to follow your local restrictions or guidelines. So that said, we can take a look at how we can suggest that you do a dry out curve. Here we have a little recipe for going about it. So how do we do the dry out curves? Well, first of all, you need to collect and bring sample to the laboratory. Make sure that you bring enough. It's no problem to bring too much, of course. So make sure that you have enough sample to perform your testing. First step to do a thorough dry out curve is to completely dry the sample and also mix it. This gives you the first place of testing. Once you have the dry sample, it goes into the sample holder. And you can see that on the right-hand picture here. It's a metal cylinder. In this case, it's open at both ends with textiles in the bottom to allow drying later on to be more efficient, a bit faster and more uniform. we need to compact the sample to the desired dry density in this case, or volume. Make note of the volume here also and record the mass. And then you can calculate the density, of course, and test the conductivity at this stage. This is your completely dry sample. So this is the conductivity of the dry sample then. First point in the diagram that we can later create. Once you have tested the thermoconductivity here at dry, the sample has to go back to the mixer and be mixed with enough water to fully saturate it. Typically, of course, a bit more water than it can take. And then you have to get the excess water out, perhaps by flipping your container upside down with a piece of cloth, allowing excess water to flow out, creating your sample with 100% water saturation. Once you have done this, sample goes back to the sample holder, compress it. If you should use the same amount of sample, the same volume. If you don't remove any sample, take it back and compress it to the same volume. So you get comparative densities, or so you can create your curve with accuracy. Sample mass should be recorded again. It should be of course, now much more than we had before because we have the water added. Compress it to the correct size as mentioned, and then we test the thermoconductivity again. And this is at 100% water saturation. So that's the final point in the diagram. Once we have that, it's time to dry the sample. You can dry the sample either sitting in the bench, slow process, but perhaps more controlled, or you can place it in an oven to more quickly dry the sample and quickly get results. But it's important to not dry it too fast perhaps, because then you might miss important information. Then on a regular basis, stop the drying process. If you're on the bench, you don't need to worry about that. You just test it on a regular basis. If you do it in an oven, sample needs to come out of the oven, allowed to stabilize in temperature, room temperature probably, and you do your testing. And this is the way you go about it. You test as many steps as you need to. It depends on how a detailed graph you need to have. And before looking at the results, I want to say that we have all the credit for this testing that we're going to see the results of goes to Morgan Virtanen, my colleague over in Canada. And we had then the Triad curve as an example here. On the right-hand side, you see the data from the sample we saw on the last slide. We do suggest that you do more than one test at each point. 3 to 5 readings, you can have the machine do that automatically. And that's just to give you a little bit of statistics for each data point. Then you start plotting these points as water saturations versus thermoconductivity. You can, of course, select instead of water saturation, you could have gravimetric water content. That's kind of interchangeable. So these are the curves that we want to find. This is the Triad curve that you should put into your report and submit to the person who needs the data. In the report, of course, there are some things that you also need to make a note of. What you see here is what's stipulated by the ASTM standard. There are, of course, many more things that you might want to put in there, but at least these things are actually required by the ASTM standard. So project information, who prepared the sample, and who performed the test. If they are 2 different persons, that should be noted. Type of material, did you recondition it, or was it as extracted from the ground? And then add a physical description of it too. You should record mass, density, and volume of the sample for each temperature. You should record how the needle was inserted. Was it pushed in, or did you use a pre-drill hole? How was it calibrated? In this case, you can just note it's factory calibrated. You should also record the transient test time. That is something that comes from, you can see that in the software, so no problem there. The temperature increase, well, we looked at that already. And of course, the thermoconductivity. The standard also wants you actually to add a schematic temperature versus time graph, and you can actually find that on the onboard software. So you can make a sketch based on that, or you can even export this data from the PC software. So that should not be too complicated. And that brings us close to the end. So let's sum this up with saying that the TLS 100 is a very easy to work with instrument. just a few pushes of buttons and you are up and running with your testing. We have integrated calibration in the needles, which allows trouble-free testing. I say here, basically, you don't risk mixing up the calibrations and getting bad results. We do have several optional sensor types for testing different types of samples and even different types of properties with a VCP needle. The instrument is very light and portable. You can bring it to the field, no problem. It also works fine in the laboratory, of course. And with several options to keep it powered, it's also easy to bring or maintain in working order. The main standard for the device is ASTM D5334, but the machine is also compliant with IEEE 442 if you have the correct needle. Results, thermoconductivity and thermal resistivity for most of the needles. You then can add thermal diffusivity to the special needle for that. The device is absolutely suitable for your technical application. That's what it's designed for, but it also works really well in many other areas, like polymers, powders, construction materials, and so on. And of course, it's an excellent device for preparing these dryout curves that we have been looking at. And with that, I would like to say thank you for attending. And I see that there are several questions that we can discuss. So I will hand the word back to Mitch to wrap this up. And yeah, thank you again.
Yeah, thank you, Daniel. Before we can move on, and before Daniel starts answering questions, we would like just to remind everyone again of our webinars in July. Once again, you can register for those webinars at thermtest.com/webinars. At this time, we will start answering questions. I'll start bringing the questions forward to Dr. Cedarkrantz, and he will be ready to answer.
Yep. Let's see. The first question then is about the needles on the screen. Okay, yeah. The device shows the detected needle. So on that screen that we saw in the beginning, we had this, we used a 150 millimeter needle. So that's why it said 150 millimeter needle. If you would swap needle, it will show the connected needle. Sample length and diameter. Well, the diameter should always be at least 50 millimeters. That's not negotiable really, because if you go below 50, the heat will travel so far that you reach the sample boundary, and then the equations break down. The length doesn't really matter as long as you have it long enough for the entire needle to be in the sample. So the smallest sample that you can have with the 100 millimeter needle would be 100 millimeter long and 50 millimeter diameter. The length is not negotiable. You can have it longer, no problem, but you cannot have part of the needle being outside of the sample. That is very important. I would say that the needles are pretty robust, but with all instruments, you get, well, the question, I should read it also, it's how robust are these needles when you push them into soil with stone in it, it's gravelly soil. Well, there is a needle, there's a dummy needle coming along with all instruments. So I usually suggest use the dummy. Even though the sensors are quite robust, it's unnecessary to gamble. So use the dummy needle to probe the dirt first, and then you insert your needle and do the testing from there. Okay, dryout curves, calculation. So the calculation is nothing strange there, I suppose. And then frozen thawed soils, is there a standard for this as well? How do you do the dryout curves? Well, I think we went through how we make the dryout curves already in the presentation here. Then frozen thawed soils, yes, that's a different story, right? You could also test. You could have a sample frozen, and you can pre-drill perhaps and test through the melting. That's doable. Just be a little bit careful if you test through the melt, because when you're in the phase change of the water in the soil melting, you do have a phase change, and during a phase change, heat is not really conducted. It's used by the phase change. So you will get a strange behavior just in this melting range of temperature. So testing a few degrees away from zero is usually advised. You can test at zero, but you might get a little bit strange results there, and that basically shows that, yes, sample is melting here. Is there any criteria for water saturation after which the thermal conductivity can be reduced? Well, These soils depend on what they operate. Well, they work a little bit different from sample to sample. It depends a bit on the structure of your material. But as you saw in the curve that we showed here, there is kind of a plateau when you have a high water content. If you go above 50, it's not a plateau really, but it's fairly much a plateau. And then it starts dropping off, and just going from 0% moisture to 10 or 20 makes a very big difference. So it's this 100% dry samples are quite a special case because they're much more insulating than as soon as you have water being added to the mixture. Yes, there will be a recording of this after it's ended. I think it will be sent to everyone attending, and then you will also be able to access it through our homepage. Maybe Mitch will add a word on that before we wrap, but that's usually the procedure.
Yep, exactly. So everyone that has signed up for today will be receiving an email at the end of the week on Friday of a recording of this webinar, as well as you can find the webinars on our websites at THERMTEST Europe, THERMTEST Latin America, and THERMTEST.com.
Okay, the next question is what causes large drift in the data when testing in the lab, and how can you reduce drift? Well, drift should not be present. If you're in the lab and if you have a stable temperature in your laboratory, if you have had the sample sitting on the bench, then you should not see any big drift. You can have drift if you do too much testing with no waiting time between your tests, because of course the needle will heat up the sample a bit. And then if you test again, the sample has started to cool when you start heating again. That can give you drift. But in general, if you test in the lab, if you leave the sample in the room to stabilize before starting testing, you should not really see drift. You could, of course, also test the sample in a fridge if that's more close to your application. As long as you have a stable temperature in this fridge, and if you wait long enough between your tests, you should not see drift. So the main way to reduce drift is wait for temperature stability. How to calculate this? Well, basically, it's just you need to find your dry density, and then you find how much mass you add from water, and then you can find the density including the water, and that's how you then you can calculate the gravimetric water content. But it's a quick Google way, I think, for you to find that, so you can actually see the equations. The splash screen that showed R2 value. Yes, the R2 value depends on if you already have an instrument. So these pictures that I showed here, this was from the version 2 of the instrument. So it's maybe more easy to find here. You have the same number also in the older devices. Then I think it's called correlation. That's really the R2 number. Thank you for the nice words.
At this time, I think, Daniel, that wraps it up for the Q&A session. Once again, I'd like to say thank you for presenting.
Yep, thank you very much, and thank you everyone for listening.
Awesome. Everyone have a great day.
Bye-bye.